Hello, and welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features, Lesson 1, Going to Pieces. For question 1, directions say, use the graph to find the indicated function value. So for part A, we're looking for f of negative 3. Well, negative 3 is right there on the x-axis. And when we plug in a negative 3, we get 0. So f of negative 3 is 0. For B, x is negative 2. Let's go ahead and just do this in black. Negative 2. For negative 2, when we evaluate negative 2, we are down there, which is 1, 2, 3, 4. So it's negative 4. For f of 0, right there, we evaluate 0 on this function. We're down there, which is negative 6. And for f of 2, that brings us to there. And we are once again back on the x-axis. And so our y value, or f of our function value, is again 0. Okay, so number 4, we have kind of a funky looking graph here, but we should be able to evaluate these values without too much difficulty. So the first question is part A, what is r of negative 2? So negative 2 is right there on the x-axis. And when we evaluate negative 2 on this function, puts us right there at the kind of the little peak, I guess, and that is negative 4. Or sorry, positive 4. So r of negative 2 is 4. Then r of negative 1, well, negative 1 is right there. And when we evaluate that on this function, that puts us right there, which is positive 1. R of 0, 0 is right there. And when we evaluate 0 on this function, we are at the origin. So our y value is also 0. And then r of 1, 1 is right there. And when we evaluate 1, that puts us at positive 1. So r of 1 is 1. Question 5. Isaac lives 3 miles away from his school. School ended at 3 p.m., and Isaac began his walk home with his friend Tate, who lives 1 mile away from the school, in the direction of Isaac's house. Isaac stayed at Tate's house for a while and then started home. On the way, he stopped at the library. Then he hurried home. The graph is a piecewise defined function that shows Isaac's distance from home during the time it took him to arrive home. All right. So we've got this graph. Our x-axis is time. Our y-axis is distance from Isaac's house. And he went from school to Tate's house, hung out with Tate, continued walking, stopped at the library. After the library, kind of hustled home and got home. All right. Part A. How much time passed between school ending and Isaac's arrival home? Well, when school ends, that's at time 0, right? So when school ends, time is at 0. And then when he gets home, time is 3.75. So if we want the amount of time that's passed between these 2 points, it's going to be 3.75 minus 0, which is obviously 3.75. And they never really specifically say hours here, but I think it's safe to assume that we're talking about hours. So 3.75 hours have elapsed. Part B, how long did Isaac stay at Tate's house? So when he is staying at Tate's house, he's not getting any closer to his house, right? To Isaac's house. So when Isaac is at Tate's house, his distance is not changing because he's hanging out at the house. It was also, according to our description here, it was his first stop, right? Isaac made 2 stops going from school to his house. He stopped at Tate's house, and then he stopped at the library. So what that means is this section right here, where his distance from home is not changing, that represents the time that Isaac was at Tate's house. His distance isn't changing, and it was his first stop. So if we want how long did Isaac stay at Tate's house, well, he left at 2.5 hours, and he arrived at 0.5 hours. So if we want the amount of time that he stayed there, it's going to be 2.5 minus 0.5. He arrived half an hour after school ended, and he left 2.5 hours after school ended. So that means that the total amount of time at Tate's house was 2 hours. Part C, how far is the library from Isaac's house? Now the library, let me get rid of all this and this. All right. The library was his second stop. And so this represents Isaac hanging out at the library. And we're looking for how far is the library from Isaac's house. Well, notice that after he leaves the library, then he goes home, right? So after the library, he goes home. And so his distance, when he leaves the library, his distance from home is 1.5 miles. And when he arrives home, I don't know why this is 0.01. It really should just be 0. But let's I think we can basically assume that it's 0. So when he leaves the library, he's 1.5 miles from home, and then he arrives home. So that means that the library is 1.5 miles from his house. Part D, where was Isaac 3 hours after school ended? Well, this is basically just saying what happens when we evaluate this function at 3, which is right there. So at 3, he was right there. And that, as we just said, was during his stay at the library. So 3 hours after school ended, Isaac is at the library. Part E, use function notation to write a mathematical sentence expression that says the same thing as Part D. So, like I said for Part D, we're basically just evaluating this function at 3. So if we want to use function notation here, we can say that this is f of 3. So f of 3. And when we evaluate f of 3, we get 1.5. And remember, the library is 1.5 miles from Isaac's house, right? So this, again, is just sort of another way of saying he's at the library. Part F, when was Isaac walking the fastest? How fast was he walking? So if we look at the graph, his different sort of time periods where he's walking Well, there was walking from the school to Tate's house. So walking from school to Tate's house with Tate. Then there was walking from Tate's house to the library. Then there's walking from the library to his house. And just by kind of visually looking at these three sections here, um, the final section looks the steepest, right? And it is the steepest. Also, the description, if you notice this, he hurried home, right? So it's almost kind of cluing us into the fact that like that's the time when he's walking the fastest. So the when was Isaac walking the fastest? He was walking the fastest at the end of his walk. And if we want to know how fast he was walking, well, he went 1.5 miles, right? Because remember, the library is 1.5 miles from his house. So he traveled 1.5 miles. And if we take a look at the times here, he left the library 3.5 hours after school ended, and he arrived at his house 3.75 hours after school ended. So what that means is it took him 3.75 minus 3.5 hours to walk the 1.5 miles. We can clean this up a little bit. So our numerator is going to stay as 1.5 for a second. The denominator, 3.75 minus 3.5, is 0.25. So we have this, and this actually is miles per hour, right? That's what we're talking about here, miles per hours, right? So it's this many miles per hour. If I want to just clean that up a little bit, we can just type that in to our calculator here. So 1.5 divided by 0.25 is 6. And so instead of leaving our answer sort of like in this weird decimal fraction combination, right, this is equivalent to just saying 6. If you wanted to do that without the calculator, it's kind of annoying. You basically have to. One thing you could do would be to multiply the numerator and denominator by 4, right? That would clear out your denominator. But like I said, if you have access to a calculator, I'd say use it there. So anyway, we end up getting 6. So he was traveling 6. He was traveling 6 miles per hour. Moving on to the set section. Question 6 says, a parking garage charges $3 for the first 2 hours that a car is parked in the garage. After that, the hourly fee is $2 per hour. So part A says, write a piecewise function, p of x, for the cost of parking a car in the garage for x hours. And the graph of p of x is shown. All right, so they're giving us a graph, and our job here is to come up with the piecewise function that represents this scenario, this graph. So we're looking for p of x, and they told us to use a piecewise function. We kind of quote unquote know that we have to use a piecewise function because we have two different sort of situations that we have to deal with depending on how long the car has been there, right? For the first 2 hours, we have like one situation, and then after 2 hours, we have a different situation. And so that's why we need to use a piecewise function. So p of x is going to equal something. And in order to figure out what that thing is, we need to sort of establish, well, what is the interval for x that we're talking about? So the first interval is between 0 and 2 hours. So another way of saying that is that 0 is less than or equal to x, which is less than or equal to 2. So if x is in this interval, then something happens. And when x is larger than 2, when x is greater than 2, something else happens. Now, when x is between 0 and 2 for the first 2 hours, so we're talking about this piece of the graph, well, that's, again, between 0 and 2. And notice that this entire time, it's at 3. Right? It almost like doesn't really matter what your x value is. As long as it's between 0 and 2, you're going to get charged $3. So P of x equals 3, a constant, between 0 and 2. Now, when x is larger than 2, well, now we're talking about this piece of the graph, and obviously we're talking about these values for x. Well, this is a linear function. It's a straight line, and we can use slope-intercept form. We don't have to get too crazy here. So what we need is mx plus b. So m is our slope, and if we can just sort of pick really any 2 points here, doesn't really matter, but we can just start, I guess, at the beginning. So from there to there, our slope goes up 2 and over 1. So our slope is 2 over 1, which is 2. So 2x. Also, that should not be that surprising that our slope is 2, because we're getting charged $2 per hour. So that's our rate of change. Every hour we get $2 additional. So it kind of makes sense that our slope would in fact be 2, because that's the rate of change for this problem. So the only thing that we're really missing here now is the y-intercept, and let me clear out all this extra stuff. All right. One way to get the y-intercept here is to say, all right, well, what would happen if I were to continue this line to the left, where it would, in fact, intersect the y-axis, right? So if I do that, what I end up getting is this continuation of the line. Now, this is not actually part of the function, right? Because now, at this point, between 0 and 2, our function is up at 3. But if we're trying to sort of figure out what is the y-intercept of this line, right? If you follow the slope here, going 2 and 1, down 2 over 1, down 2 over 1, you do in fact end up getting -1 for the y-intercept of that line, right? It would be -1 if we were to extend it. So that's one way to get the y-intercept here, so 2x minus 1. Another way to get it is to just focus on a point on the line. We can say maybe just our initial point. And notice that when we plug in a 2, we get a 3. Plug in a 2, we get a 3. Well, before we added our y-intercept here of -1, if I take it away for a second, right, 2x, well, when I plug in a 2 right now, I get 2 times 2, which is 4. But I don't want 4, I want 3. And so that's another reason why we subtract 1, just to sort of make it work, essentially, right? We know what we want. We just have to come up with an equation that fits that. So a couple different ways for you to get that -1. But anyway, here is our piecewise function. Part B, what is the meaning of P of 1.5 for this situation? All right. Well, 1.5 is right there, and that puts us right there. But that's actually even more work than we had to do, because all we really have to say is just sort of say what for this situation, what is this asking, right? And so P of 1.5 means to find the price at 1.5 hours, which we happen to know is going to be $3, right? So if you were to evaluate P of 1.5, you'd get 3. And ultimately, what that means, again, is we're just saying, well, what is the price at this input of 1.5 hours? Question 7. Lexi completed an 18-mile triathlon. She swam 1 mile in 1 hour, bicycled 12 miles in 1 hour, and then ran 5 miles in 1 hour. All right. They are giving us a piecewise function here, L of t. Not surprisingly, we've got 3 different pieces because we've got 3 things going on. We've got swimming, then biking, then running. So 1, 2, 3. Part A, create the graph of the piecewise function L of t. All right. Well, we're going to need to make a graph here. Normally they give us a graph. I don't really know why they didn't this time, or at least a coordinate plane, but it's all right. We've seen this now multiple times where in a lot of real world scenarios, again, not all, but in a lot of real world scenarios, negative numbers don't really make sense. So we're going to position our x and y axes here really just to kind of focus on the first quadrant. Because in quadrants 2, 3, and 4, there's negatives, but negative time and negative distance doesn't really make sense here. So we're just going to focus on quadrant 1. So we've got 3 sort of pieces here that we've got to graph. There's one segment is from 0 to 1. So we'll make that 0 to 1. Then we've got another segment from 0 to 2. And then another segment, from 1 to 2, and then another segment from 2 to 3. We're also we're told that this is an 18-mile triathlon, right? So even without necessarily doing any of the math, we sort of know that our highest y value is going to be 18. If we want to sort of calculate that, what we could do is we could actually take the third piece. We could take the third piece of our function here and plug in our final number. And if you plug in a 3 into 5t plus 3, you do in fact get 18 because that's the end of this race, right? But again, the description tells us it's 18. So our top value needs to be 18. So let's see, I'll just maybe go by 2s, and I think we should be able to fit 2, 4, 6, 8, 10, 12, 14, 16, and 18 is at the very top. Just clean this up a little bit. Actually, I guess I can always just extend this line. There we go. Just do, oh, that's a little too much. Okay. All right. And 14 and 16 and then 18 will go right there. And this is my y-axis. All right. So these are my coordinate axes. And the first piece is just L of t equals t. So that is a linear function with a slope of 1 and a y-intercept of 0. So that tells us that we're going to go from 0, 0, right there-ish. Maybe do that a little bit better. Right there. And then we're going to go to 1 comma 1, because when we, when you take a 0 and plug it in, you get L of 0 is 0. And when you take a 1 and plug it in, L of 1 is 1. So our endpoint here for the first segment is going to be at 1, 1, which is right about there. And we can actually connect these. Just like that. All right. That's our first piece of this graph. The second piece is between 1 and 2. And again, we have a linear pattern here. 12t minus 11. That is definitely a linear function. And I think probably the easiest way to do this problem is to just take the endpoints of our interval here and plug them into the function and just evaluate it, right? So if I'm taking a look at this first, the first one is 1. Now technically 1 is still in the first interval because t is less than or equal to 1, and then in the second piece it's 1 is strictly less than t. But we also are expecting this function to be continuous, which means even though t is technically in the first interval, we're still going to use the 12t minus 11. We're still going to use the second piece, and we're still going to evaluate it at 1 because, again, we're not expecting there to be any gaps in this function. So it should still be essentially the same thing as what we got in the first interval. And it's easy enough to check that. So if we plug a 1 into this equation here, we get 12 times 1 minus 11. Well, 12 times 1 is 12, and 12 minus 11 is 1. So we're still at the same point. Even though we got it in a different interval, we, not surprisingly, are still at the same 1 comma 1 point where we left off with the swimming. And now with the cycling, it's the same distance. If we take the other interval, or the other endpoint here, the 2, and plug it in, well, when we plug in a 2, we get 12 times 2 minus 11. So 12 times 2 is 24, and 24 minus 11 is 13. So what that tells us, getting back to the graph here, is that when t equals 2, we would expect Lexi to have traveled 13 miles. So it's all the way up there. And again, this is linear. So we, again, would expect this to be a straight line. Oh, come on. There we go. All right. And that's that second piece. Third piece is again linear, 5t plus 3. If we plug a 2, like we're expecting this to be 13, and it is, right? 5 times 2 is 10, plus 3 is 13. So again, we're sort of picking up right where we left off. This last section is running. And then the second endpoint here is 3. And if we plug a 3 in, we get 5 times 3 plus 3. Well, 5 times 3 is 15, plus 3 is 18, which is the end of the race. So at 3 hours, Lexi is right there. And if we continue our function, it looks like that. And so that is a graph of our piecewise function for this triathlon for Lexi. Part B, what is the meaning of L of 2.5 for this situation? Notice that they're not asking us to evaluate L of 2.5, right? L of 2.5 is, it's on our graph, it's like right there, right? but they're not even asking us to evaluate it. They're just saying, well, what does this mean, essentially? And what this means, this one I'll use the typing here. So L of 2.5 means to find the distance. Change the size of this thing for a second. Okay. Okay. L of 2.5 means to find the distance Lexi has gone in 2.5 hours. We could evaluate that, but it's not necessary, so we're good to go. All right, question 8. Question 8 says, use the piecewise function showing the amount of money that will be charged, C of P, for a group to go to an amusement park based on the number of people P in the group. So C of P, we've got 4 different intervals here. And again, this is all depending on the number of people that are in the group is going to affect the price to admit that group to an amusement park. All right. So let's just dive right into the different components here. So 8A says find C of 25. All right. Well, in order to do that, we sort of need to figure out, well, which interval are we talking about here, right? If we have 25 people, where does that sort of fall? What rate are we going to get charged? What part of this piecewise function? What piece of this piecewise function are we talking about? Well, 25 is between 20 and 30, right? So 20 is less than 25, which is itself less than or equal to 30. So we're talking about our third piece here, and our function says that when you're in that interval, C of P is 45P plus 300. So we're just going to say C of 25 is 45 times our input, which is 25, plus 300. Okay. Get out your calculator, you can evaluate that. We end up getting 1,425. So that group is going to get charged $1,425 to admit a group of 25 people to the park. Part B, explain how each part of this statement fits with the situation. So we have C of 16 equals 980. So there's nothing to really solve in this question. The result is that, if you have 16 people, you're going to get charged $980. But this question is saying, well, just sort of make sense of this. What's going on here? What does this all mean? So C of 16 means that there are C of 16 means that there are 16 people. The 980, the result, means the cost will end up being $980 for those 16 people. All right. Part C, how much will it cost for a group of 23 people to go to the park? So we have 23 people. And again, in order to evaluate this, we just need to figure out, all right, well, what piece are we talking about? What interval contains our input of 23 people? It actually turns out it's the same interval as before. It's the same interval as part A. So again, we're going to use the same piece of this piecewise function because for 23 people, that 45p plus 300 represents the pricing structure for a group of 23 people. So we are essentially looking for C of 23. C of 23 is 45 times our input, which is 23, plus 300. Again, leave it to you to evaluate this on the calculator, but we end up getting 1,335. Now, this question was asked in the context of the scenario. So when you give your answer really should be in the context, and we're talking about dollars here. So your answer here is $ 1,335. Because again, the question was phrased in the context of the question, not simply just evaluating the function, but how much does it cost? Part D, how do you know which piece of the piecewise function to use when calculating the price for a given number of people? Well, we've kind of already alluded to this. So the intervals on the right all involve these inequalities. And so the inequalities, okay, next to each piece, get the font to a more reasonable situation here. All right. So the inequalities next to each piece provide this guidance, right? What we're kind of looking for here. So what we got to do is we got to find which of the intervals your input value falls into using the inequality, and then use that piece to determine the output. Right? So we examine the intervals on the right using the inequalities. We identify sort of where we're, quote, supposed to be, and then we simply use what's on the left to actually evaluate the function. Our last several problems appear in the Go section, and directions here say, use the given information to write the equation of the line in point-slope form. Our good friend point-slope form makes a return. Graph each line. So point-slope form, as the name implies, contains a quote-unquote random point in our function, in our linear function, and the slope. So that's why it's called point-slope form. It contains a quote random point and the slope. And as a reminder, point-slope form looks like this. Y minus y1 equals m parentheses x minus x1. M is our slope, as always. And our, quote, random point has the coordinates of x1, y1. So the x's and the y's that have this subscript of 1, that's the point. That's the information that we're given. The x and the y without the subscripts are your variables in the function, right? Just like, y equals mx plus b has an x and a y. Point slope form also has an x and a y that change depending on, the input or the output. But the ones with the subscript, the x1 and the y1, those are just numbers that don't change because they're based on the point that you're given, or however it is that you get that point. So for number 9, we're told that we have a point of 1, 2, and that our slope is 3. So for point slope form, we simply take our sort of general formula here and plug in what we know. So this first y does not have a subscript, so it stays, right? We're coming up with an equation, so we don't want to plug in for like all of our letters, right? We want to be able to sort of have a usable function here. So we're going to have y. Now it's y minus y1. So our point here, we have x1 and we have y1. So y1 is 2, and again, we're subtracting it. So it's y minus 2 equals m. Well, we're just told it's 3. It's pretty straightforward. parentheses, this x, we do not substitute for it. That's our input to our function. And then x1 is positive 1, and we're subtracting it, so it's x minus 1. All right. Excuse me. So that is our equation. If you want to, this is not necessary. You could bring that that -2 over to the right, just so you have y equals, right? So if you bring that -2 over to the right, you get y equals 3 parentheses x minus 1 plus 2, right? If you're subtracting 2 on the left and you bring it over, it becomes a plus 2 on the right. But if you left it in the original form, that's also fine. All right, so we want to graph this. Well, we're told that the point we're told that the point 1, 2 is on our graph. So let's not like make this overly complicated. Let's use that point because it's on the graph. So I think we should be able to keep a scale of just one box here. So we'll just do 1, 2, 3, and 1, 2, 3 here, x and y. So 1, 2 is on our graph. So 1, 2 is right there. All right. Now our slope is 3. What that means is from this point, we should be able to use our slope, our rate of change, rise over run, to get additional points. Whenever you have an integer slope, you can always put it over 1. So 3 is really 3 over 1. So from this red point here, if I apply my slope of 3 over 1, I'm going to go up 3 to the right 1, and I get a second point right there. I could stop there because 2 points determine a line, but it's not that difficult to get some additional points here if I want to. From my original point of 1, 2, I can also go to the left. Now, with a positive slope, if you go to the left, it means you're actually also going down, just to sort of make the graph work out. So from 1, 2, if I go down 3 and to the left 1, I'm there, which also happens to be my y-intercept. So this function has a y-intercept of -1. And if you were to simplify this, you would get that. You would get the -1 as your y-intercept. Continuing, if we go down 3 and over 1 again, we get right there. And so if we're going to graph this, it's going to look like that. And that is that's our graph. The next assigned question was number 12. All right, question 12 has a different set of directions. So for 12, write the equation of the line, again in point-slope form, that contains the given points. Then sketch the graph of each line. Once again, point-slope form, y minus y1 equals m parentheses x minus x1. And this time we are given 2 points. And we want to come up with an equation. I'm going to do this a little out of order. I'm going to actually graph it first because we're given 2 points, and that's actually 2 points are sufficient to graph. And so K is at the origin, 0, 0. So that's right there. And then L is -4, 5. So we might as well keep, again, a simple scale here, 1, 2, 3, and 1, 2, 3. Each box is worth 1. So in that case, -4, 5. I go to the left 4, I go up 5, and I'm right there. So if I want to graph this, I can actually do this right now. So if I take my line here, and I just do that. All right, well, that's my graph. And so now all I'm missing is the equation. Now it says to write it in point slope form, and that's fine. But notice that they actually didn't give us the slope. We don't have m. Now, there's a couple different ways that we could get m. Notice that, first of all, we have a graph, and we could get our slope from the graph, right? We could pick any 2 points on this graph, find the rise over run, and we would get our slope, which we could, relatively easily do. We can also recognize that slope is, as always, the change in y over the change in x. It's the rise over the run. And formulaically, this is y2 minus y1 over x2 minus x1. And the 2 points here are 0, 0, and negative 4, 5. So y2 is 5, y1 is 0, x2 is negative 4, and x1 is 0. 5 minus 0 is 5, and negative 4 minus 0 is negative 4. I'm going to pull the negative out front. And so our slope here is negative 5/4. And again, you could have easily gotten that from the graph as well. You would have gotten negative 5/4 for the slope there as well. So now we just need to write this in point slope form, and we can use either point. We have 2 to choose from. If I choose my first point, the origin, well, that becomes y minus 0 equals negative 5/4, parentheses, x minus 0. You can clean that up if you want. Or we could use the second point. So the second point would give us y minus 5 equals negative 5/4. That doesn't change, right? The slope is the slope. And then x plus 4, because we're subtracting a negative 4, all right? So it doesn't really matter which one you use here. And if you want to clean them up, you're welcome to, but either one of those would be an acceptable equation. All right. Last question was number 13, same directions. And our points are negative 1, comma 7, and 3, negative 1. Again, I'm going to do this a little out of order. I'm just going to plot my points. Now, one of our points has a 7 in it, and we've only got 5 boxes in each direction, so we're going to have to use, we're going to have to double up here. So 2, 4, 6, 2, 4, 6. That's just to make sure that we can actually graph both of our points. So the first point was negative 1, comma 7. So negative 1, comma 7, I'm going to go to the left 1 and up 7, and that puts us right there. That's negative 1, comma 7. And my other point is 3, negative 1. So 3 means I go to the right 3, I go down 1 because it's negative 1, and that puts us right there. And again, 2 points determines a line. So if I want to, I could simply graph this line from these 2 points right there. And I can go ahead and just clean it up a little bit. And that's my graph. So now, again, the only thing that we're missing is the equation. And again, we want to put this in point slope form. We don't have the slope, not yet. And this time, I guess, unlike 12, for 13, I'm actually going to, I guess I should have kept my points here because now I'm going to use them. So I had a point there, and I had a point there. I'm going to get my slope this time. I'm going to do it from the graph, just to mix it up a little bit. So to go from the point on the left, I'm going to go down. So I'm at 7, and I want to go down to negative 1, right? So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So my rise, and I went down, so my rise is negative 8. Okay. Then my run, well, I'm at negative 1, and I want to get to positive 3. So that's 1, 2, 3, 4. So my run is 4. So I have negative 8 over 4, which is negative 2. And if I had applied my slope formula, y2 minus y1 over x2 minus x1, I would have gotten the same thing. I would have gotten negative 2. So now I just simply plug it into point slope form. And again, I can choose either point here. So if I choose x, point slope form becomes y minus 7 equals my slope, which is negative 2, parentheses, x minus negative 1. But I don't want to say minus negative, so I'm just going to say plus 1. Okay? Essentially, the sign flips with both x and y. Or I could use my other point. So if I use my other point, it's going to be y. So it's going to be y minus negative 1, which is actually plus 1, equals, my slope doesn't change, it's still negative 2, and it's going to be x minus 3. So these two equations are equivalent. They say exactly the same thing. They just look different. And if you were to simplify them, you would in fact get the same exact, same identical equation.